All right, welcome back. If you haven't yet, there is a first part to this recitation where we finish amortized analysis, do the couple of last examples there that we haven't done last time. Uh, so I highly recommend going and watching that. This recitation, we're going to go over linear data structures, um, which is a really cool and fun recitation. It's one of my favorites. It's very algorithmic. There's a lot of cool questions, and we see a bunch of answers and riddles. Um, it's fun. It's makes you think. Very fun, very cool recitation. At the end, we're also going to do a question using union find, which you learned in the lecture, and I thought it was very important to um, use it in a real question and kind of go over it. So let's jump right in. So today we're going to be doing linear data structures and union find. Okay, so this is exactly what I just said. We're doing, first we're going to do some questions with arrays and then some linked list, both of which are linear data structures. And then we're going to go into union find. Now, a quick reminder, what is a linear data structure? It's a data structure where the data is saved linearly in, you can think about it that trees are not linear because you can't go from one element to the next um, and traverse the whole data structure, visiting only element at most once. Right, for a tree, you have to go back to certain elements and then check the left node and then the right node, and it's not saved in a linear manner. A linear manner is that you can traverse the whole thing, um, seeing each element only once. Okay, so now let's jump right into it. First, a little reminder, an array is um, is consecutive cells in memory. If you want to access a specific cell in the array, it's in O of 1 time because you can just do pointer arithmetic and jump to the exact spot that we need. Um, okay, searching an element within an array. If it's just a general array, you need to check every single element, therefore it's O of n. In a sorted array, we can do, as we learned in previous recitations, you can do binary search. We're going to see um, another type of search on a sorted array in this recitation. Very cool, called exponential search. Um, and also it has a static size, right? We can't change the size after runtime. Whenever we um, initialize an array, we have to initialize it with the size. Now, we did learn how to do a dynamic array, but how the dynamic array works, if you remember from amortized analysis from the previous lecture, you have to copy the old array into a new array with the new size. So really, the arrays are static, and the dynamic array is really just a data structure that copies the old array into a new array, and therefore you can change the size. All right, first question, binary search. Given uh, an array, an assorted array A from 1 till n, and number x that appears in our array, let's denote k, the index, the minimal index, such that ak equals x. It could be that it appears a couple times, but let's just denote the first one as k. So here for in this example, for searching for 12, then the index is 0, 1, 2, 3, 4, 5. Or if you start it from one index, then it's k equals 6. So I guess we're doing one index here. All right. Now propose an algorithm that finds the index in time of log n, which we know already is binary search, and then also propose a different algorithm that does it in the minimum time of k or log n. So therefore, um, it does it whichever one's shorter. If it log n is smaller, then it does it in log n. If k, the index is shorter, it does it in k. And O of log k, we'll see how to do that. All right, first one, binary search. We know this from previous recitations. Every time we're gonna, in a divide and conquer manner, we're gonna delete half of the array. We're gonna look at the middle element, compare our our number that we're searching for to the middle element. If it's larger, then we search on the larger half. If it's smaller, then we search on the smaller half. So let's say here, we're searching for an element that's bigger than 7. We're looking in this example for 12, so it's bigger than 7. Then we look at the next middle. Let's say we round up. So this is the middle. We take the higher of the two medians. So 17, it's smaller. We delete the upper half of the array, and then we look at these two. 15, not 15 is less than, and 12, we found it. So therefore, we return the index of this element now that we found the element in the array. And that can be with just simple pointer arithmetic. But you really, as you run along, you have the index I. So really, when you access this, you have an index I, and you just return it. All right, so this is pseudocode from Wikipedia. You can go over it if you'd like to. Just an important little note is that really we learned how to do this with divide and conquer, but and recursion, but you can really do it with a while. Most recursions, you can do it with just loops. Sometimes it's more elegant with recursions. Sometimes it's more elegant with loops. Here they did it with loops because it is a little bit more intuitive to do it with loops. All right, now how are we going to do it in the minimum of k or log n time? So this is a trick that's really important to know. I think we did it in one other place, but it's that we take two algorithms and run them simultaneously. And then if we run them simultaneously, at each step, we perform a step in each algorithm. Therefore, the second we get to an answer in one of the algorithms, we stop the other one, and therefore it's the minimum of the two algorithms. So O of log n we've seen, this binary search. O of k is trivial. We just traverse the array until we find the correct element. And we're just gonna run them simultaneously, and we'll stop both algorithms the second one of them finds it. So let's just see an example. This one, we're looking for 12, so we'll run them both, right? In this one, we cut the array in half. We search in the upper half. In this one, we just search element by element, and we stop when one of them finds it. So we don't continue all the way, because then it would be the maximum between them two. We stop both algorithms the second one of them finds it. Therefore, it's the minimum of the two algorithms. And since basically we run them simultaneously, it is O of 2 times the minimum of both of them, because in this example, we run it log n times. So we run this algorithm log n times. We also run this element log n steps. Even though we didn't finish it, we still run it log n steps. So it's just 2 times that, which is still asymptotically just the minimum of k and log n. We don't care about running it simultaneously. Therefore, you can run any amount of constant algorithms simultaneously and still obtain the minimum of all of them. So just a cool little trick. Now, what we're really trying to get to is exponential search, like I hinted at earlier. So this runs in log k. Reminder, k is the index, right? Here it runs in runtime k, minimum of k and log n. K is the index of the set element, so that would be here. Okay, so let's assume that the array is an infinite size, and any missing elements, because the array technically like stops and doesn't have any more elements, but we're just going to look at it as if it was infinite, and all those elements will be infinity. Now let's search the first element, which is a power of 2, and the value is at least x. So we're going to look for, we'll see the example here. So we want to find the power of 2, the first power of 2 that's bigger than the element we're searching for. So if we're searching for 12, we want the first power of 2 that is bigger than 12. So let's just see an example. So here we search for 2 to the power of 0. We see it's not bigger than 12. So we continue to 2 to the power of 1. We see it's not bigger than x, which is 12. So if we keep on searching, 2 to the power of 2, 2 to the power of 3. And now we see that this is bigger. So therefore we know 12 is within this part of the array. And this whole part we can ignore, right? We can just ignore it, delete it, kind of like binary search. But here we search in exponential manner. each time 2 to the power of I. And now the claim that we're going to prove is within log k rounded up steps, we will remain, right, because we know it's smaller than the 2 to the power of this log k element. We know it's in this half, so this element, this array that we remain with, is at most 2 times k minus 1. We're going to see the proof for that, but you can kind of view it as this is the element, 12 is the kth element, right? So therefore, if we times this by 2, we know that we're going to pass that same 2 to the power of I, right? If we have this as the kth element, which is the 6th element, right? So therefore, it's greater than 2 to the power of 2. If we times this by 2, it's definitely greater than 2 to the power of 3. If that was a little bit of an intuition, but let's see it proved formally. The search stops at some sort of power of 2. That's denoted by 2 to the power of I. Remember that place it stops, it's larger than x that we're searching for. And now we know that k is between 2 to the power of I minus 1 and 2 to the power of I, right? It's between 2 to the power of I minus 1 to 2 to the I. Now let's just take the first side of the inequality, and that's times it by 2. So therefore we get this part times by 2, which equals 2 to the power of I. We want an upper bound for 2 to the power of I. That upper bound is 2 times k. Now, in order to get to the actual argument, the actual claim here, we need to change it from strictly smaller to smaller equal and minus 1 here. And that's how we get to 2 times k minus 1. But here it doesn't really matter because all we want to really show is that it's O of k. That's our main, that's what we're trying to prove. So if you want to prove the exact claim, you have to do here, you have to change this to smaller equal and minus 1. So therefore we get 2 to the power of I is smaller, strictly smaller than 2 times k, or smaller equal to 2 times k minus 1. And how many jumps have we done? Jump is increasing I. We do I jumps. And it holds that I equals log 2 to the power of I, because this is just by definition, by log rules. This equals I. And we know that this is smaller than log 2 of k. We just applied a log to both sides of this equation, right? Log 2 to the power of I is this side, and log 2 times k is this side. And this equals to log 2k plus 1, which is O of log k. So the amount of jumps we've done is log k plus 1, which is O of log k. Now let's assume that the array, the sorted array is infinity, right? And all these extra elements out of the screen that don't exist are going to be infinite. That's what we just said before. So this is the claim that we just proved, right? We kind of proved it for 2 times k, but you can also prove it, it's smaller equal than 2 times k minus 1. And now on that remaining array, which is the size of 2 times k minus 1 or 2 times k, it doesn't matter, it's O of k, we're gonna do binary search on that smaller array. So we find first 2 to the power of I that is bigger, the first one that's bigger than k, than x, and then we binary search on that array, right? So now that we have this array, we're looking for 12. So this is 2 to the third power, which is the first 2 to the power of I, which is bigger than 12. And now we take that part of the array, and we want to binary search on it. So we take the middle element, and as we know, we just regular binary search until we find k. Now, to sum that whole algorithm up, within O of log n steps, we are left with an array that is the size of O of k, right? We check for 2 to the power of I that's bigger than x, and then we ignore the rest of the array, and we only do binary search on the part that is less than 2 to the power of I. So now we're going to do binary search on that next part. And it happens because the array is O of k, it happens in log k runtime. And therefore, in total, we do O of log k here, O of log k here. Total is O of log k. All right, let's move to the next linear data structure that we all know and love. Linked list. Every element is has some sort of content, has some sort of fields in it, and also has to include a pointer to the next element in our linked list. We can scan the linked list in linear time, right? We have to check every single element to scan it. We can also very easily insert or remove elements. We can insert them very easily from the beginning in O of 1, or we can have a pointer to the end and insert it in O of 1 at the end. And we can also, if you have a pointer on a specific element, you can remove it in O of 1 if it's doubly linked list. If it's not doubly linked list, you can remove the last one, like the first one in O of 1, because you just skip with our pointer to the linked list. You just skip to the next element. But if you want to remove something in the middle, you have to have a doubly linked list, and then you can remove it and change the pointers of its neighbors to point at each other. But note that to access some sort of element in the middle, if you're not given a pointer to it, you have to loop through the whole linked list. Therefore, it's O of n, which is much worse than a regular array, which is O of 1 to access a specific index. All right, so let's do a problem. Let's solve a problem together. We're given two linked lists of different sizes. And we know that there's a specific point that the two linked lists merge into one linked list. As follows, we want to find the point where they merge, the first point where they merge, in these times. So we're going to go through them again, one by one, and we're going to show algorithm that can do it in those runtimes. Also, it's important to point out that K, L, and N are not given to us. We're just given heads to the linked list. So we don't know how large each one is. Now, if we did know how large K, L, and N were, then what we could do is just, and this is actually the first algorithm, is you just take the larger one. If k is larger than L, you just start from k, do k minus L steps, and then they're both going to be in the same place. And then you continue moving both of them by one each time until the element becomes the same element. And we'll see that in a second. So the first one, that's if we know k, L, and n. If we want to know k, L, and n, we can do that. We can just scan our linked lists and find the size of k plus n. Find the size of L plus n. As such, we just keep a counter. Here, I'll just show you the animation again. We just go through the linked list, keeping a counter, and then we know the size of k plus n, and the same thing for the L2 for the second linked list. Now we know the size of the second linked list. It's L plus n. Now what we can do is we can subtract one from the other to get k minus L. And therefore, we know the difference between k and L. If we know the difference between k and L, we can do the trick that we said earlier, and we'll see it in the animation, which is move the larger one, that k minus L amount, and then they're both going to be starting at the same distance away from x, and we can move each of them, we can increment them by one each time. So that's, now that we know k minus L, we'll then move the bigger one, the larger one. Let's just assume, without loss of generality, that k is larger than L. So we'll move k, we'll start scanning this and move it, our pointer, move it k minus L steps, and therefore also here, we both start at L distance away from x, and then we'll scan both of them simultaneously moving each one by one and comparing the two elements. The second we get to the two elements that are equal, that are the same element, we know we have found x. So let's just see an example. First, we scan the larger one um, up until k minus L times. So now the distance is L and the distance here is also L. And then we scan them both simultaneously, and each time checking if they're the same element. Once we get to the same element, we know we've found it. So that's very straightforward. Now let's try and do it in O of D squared. What is D? D, first off, is, let me go to the beginning. D is the max of K and L, right? D is the larger one of K or L. So here it's K. So really this would be O of K squared in this case, but we don't know which one is larger. That's why we denoted D to be the larger one. Let's go back to ours. Okay, so let's assume we know that K is larger than L, and therefore D equals K. We'll operate in iterations. At each iteration I, will compare the ith node in the bigger of the bigger one with every single I first element. So we're going to compare this element, the first element, to the first element here. Then we're going to compare the second element to the first two. Then the third element to the first three, and so on and so forth until we, in the bigger array, we get to x. We compare x to the first k elements. And we know that because this one's shorter, we definitely will compare this one to the same element in L2. And therefore, we can find this in, we'll see the runtime soon, but D squared. So we compare the first one to the first element, and we compare the second one, only the second one, not the first one. We're done with the first one. We know it's not that one. Compare the second one to the first two. And if one of these is equal to this one, then we know we found our merged. But we know here, because we see the whole thing, we know that it's not that, and therefore we know it's not the second one, because if it was the second one, we know this one's larger, so one of these would have to be the place where it merged. So we do the third one, and so on for the fourth one. And now note that even when we're on this one, we traverse L2 and we do pass X, right? Because we know L2 is smaller. So there will be some elements here that will pass X, but we'll only find it once we get to the element X on this in this loop, right? So we traverse X again. Well, we traverse L2 and pass X, but now when we traverse X, when we compare the two elements, we will find that X is in fact equal to X, and therefore we are done. This is the same element, and we are done. And now the runtime of this is just for the first element, we do one iteration here. For the second element, we do two. For the third element, we do three, so on and so forth until the dth element, which is our element that we're searching for. And then for that one, we're going to do not exactly D on this one. We're going to do actually the smaller one. But let's just assume, by the smaller one, I mean if this one's K, then this is L. So for the dth element for K here, for X, we're actually only going to do L iterations. So really this last one is L, but the one before it is actually, we're going to do D minus 1. So they just increased this for just for the analysis sake, but really it's smaller equal to this series, which we know because we've done it many, many, many times before, is theta of D squared. All right, so we saw this algorithm. Now let's do also, just first before we go on to the next one, it's important to note that for we assume that we know that K is larger or equal to L, right? In order for the algorithm to work, though, we really need K to be larger than L. So how can we deal with the case where L is larger than K? So we're just going to run it. This is a sign here. We're going to run them simultaneously, exactly like we did with the minimum of K and log K in the search. Here we're going to run two algorithms simultaneously, but each of them handles a case where one is larger than the other. When one of them returns the result, we'll stop the other one. Therefore, it will be 2 times d squared, but is still theta of d squared. Now, the optimal algorithm is, let's assume again that k is larger than L, therefore d equals to k, because d is the larger of the two, so d is equal to k. We're going to do iterations, but now instead of increasing each one, checking each element, we're going to do something very similar to binary search, sorry, not binary, exponential search, where we're going to check each element that's 2 to the power of I. So here we're going to check 2 to the power of 0, and then 2 to the power of 1, and so on and so forth, and each time checking all the elements here to check if they're the same. So this way, we're going to find some element. It might not be x, it might be further down the road than x, but we're going to find some element that's the same. And then we're going to know exactly like exponential search that we can ignore the rest of the linked list and we can just search on the previous part. So let's see how this would work. We search each time 2 to the power of 0. We search the first element, 2 to the power of 1. We search the first two. Then we search 2 to the power of 2. And then 2 to the power of I minus 1. We search then for this element specifically, we search for the 2 to the power of I minus 1. And then for 2 to the power of I, for this element, we'll search each element up until 2 to the power of I, which will be somewhere here, and we'll find really this element y. We might not find x, but we'll find y. Now we know that x is in between 2 to the power of I minus 1 to 2 to the power of I, exactly like we did in exponential search. So first, a claim is that in this way, we'll find y, which is to the right of x, and its distance to k, to x, is at most k, which is the larger one of these. So if we just show that here, it's just 1 plus 2 plus 4 plus 2 to the power of log k. Right, that's the one that we're going to search for here, rounded up. That's 2 to the power I. I is log k rounded up. And if you take all of these distances, it's within, I'm sorry, this is just the runtime. The runtime is 1 plus 2 plus 4 plus whatever plus 2 to the power of I. And this I that we know is log k rounded up because that's, this is the distance k. And so log k would be exactly here, but we're checking the natural number, so we check 2 to the power of log k rounded up, which would be this element. So the total runtime is O of 2 to the power of log k, which is O of k. So the runtime of this part of the algorithm is O of k. But what I was trying to explain before is that now we want to check what the distance is between the start of the linked list up until y. We know that distance up until x is k, but we need to know what is the distance up until y. So let's denote the place where it stops as 2 to the power of I. And now let's note that the index of x is k plus 1, right? It's the index right after k, which k is k is this, so it would be k plus 1. And now we know 2 to the power of I minus 1, exactly like exponential search. K plus 1 is in between 2 to the power of I minus 1 and 2 to the power of I. So let's take that first side of the inequality and let's try and find an upper bound for 2 to the power of I. So we times this part of the inequality by 2. We get 2 to the power of I is bound by 2 times k plus 1. So how many jumps have we done? We've done same exact arithmetic as earlier, but I equals log 2 to the power of I. Log rules, smaller equal by this inequality. We apply log to both sides. And log 2 of k plus 1 is log k plus 1 plus 1, which equals to log O of log k. So now that we have this, let's go back to our algorithm, because now we know that the distance, this is the important part, the distance 2 to the power of I, that's the y that we found, the place of the index of y that we found, is bound by 2 times k plus 1. All right, so remember that. Um, Now we know that this is bound by 2 to the power of k plus 1, like 2 times k plus 1. So we know that this whole thing is smaller than 2 times k plus 1. Therefore, we can say that this distance is smaller equal than k, and that helps us run the algorithm, the first algorithm that we saw, which runs in time of k plus l plus n. And now n is this whole thing, which we've bound. This isn't completely correct, because from what we found, this index is smaller than 2 to the power of k plus 1. Sorry, 2 times k plus 1. So therefore, this is actually smaller equal than k plus 1, or k plus 2. But we don't care because we want to see that it's within O of D, right? We want to check this whole thing that the distance n or n tug here is in O of k. So we do know that it's O of k because it's 2 times k plus 1. So we know this is O of k. L is smaller than k, therefore it's in O of k. And k is obviously within O of k. Therefore, these all together, the runtime of our first algorithm, where we just checked the distance of them both and then incremented this one up until here and then increment them both at the same time, that one would run in O of d time, which is O of k. So I think there's an example. There's no example here, but it's just running the algorithm from the first one, where we check the distance up until y, check the distance of L up until y, so it would be k plus, let's denote this as n tug, so it would be k plus n tug, and here would be L plus n tug, and then we do the subtraction, we know the distance, and then what we do is we increment the larger one by k minus L, which we calculate, and increment them at the same time, always comparing, checking that they're equal until we get to the equal element. All right, so then total runtime, does it say it here? No, it does not, but it would be O of D for this part of the algorithm for the second part, and also O of D for the first part of the algorithm where we find y with exponential search. So that's a really cool use of exponential search to find where two and this merge. Now, next question. Finding a circle in a linked list. So we are given a linked list, a single direct, like we don't have double directional pointers. We only have single directional pointers with n elements. And it could be that the last element is connected to some sort of element and creates a circle, a cycle. So let's just look at this example. We have a linked list, keeps on going, and this last element is actually connected to some sort of element on the linked list, which forms a circle. So therefore, you wouldn't be able to know when the linked list ends because it would go on forever. So we want an algorithm that can detect this case where we can detect that there is a cycle. And also, we want the algorithm to find that place, that first element in the cycle, because then you can split it up and fix the linked list or whatever you want to do. But our algorithm is to find if there exists a cycle and also the first element in that cycle. Okay, so first stage, if we are allowed to use extra space, we can just every element that we visit, we mark it as visited, and then the second we reach an element that we visited already, then we know that there's a cycle. Now, the runtime of this is O of n because we traverse the whole linked list just one time. But we need O of n extra memory. We need some sort of flag or bit for every single element. Therefore, it's O of n extra memory. Now, in this question, we're going to want to now solve it without any, without linear space. We only have constant space. So we couldn't use this solution, even though it's very good if you have that space. But let's try and solve it without um, the linear space. All right, so first one, let's do it in O of n squared time. Denote I. The ith element is the element that we get to after doing I increments. So if we traverse this, this is the first element, second element, third element, so on and so forth. This one will be the fourth, fifth, the sixth, seventh, eighth, ninth, because it's the sixth element that we get to if we traverse it. Now, note that this one is also the 10th because we also get there 10th. Technically, this one is the 11th until infinity, but let's just stop at the element that we already visited. And this is just to denote. Um, and then we're gonna note that if it's circular, there's one element with two different numbers. Like we just said, it has 6 and 10. There's an I1 and an I2, I1 smaller than I2, such that I2 is also equal to I1. All right, so if the length of the linked list is at most n, then we have some sort of I which is smaller than n plus 1, such that the element, the ith element, is also the n plus 1 element. So in this example, the sixth element, 6 equals, like I equals 6, is also the length of the list, which is 9 plus 1. It's also the 10th element. Every single iteration of our algorithm will continue until the jth element, and we're going to guess that j equals n plus 1. For every j, we'll search if there's an I um, that is correct, that is smaller than our j, but also the jth element and the ith element are both the same. So sorry, that was a little bit unclear, but here we assume that every iteration from j equals 1 until and so on until we find it, we're going to assume that we're going to guess that this one is really the element. So therefore, we have to check all the elements before and check if one of them is equal to this element, right? So if, let's say for this example, for this element, we check, is this element equal to this one? No, continue onwards. For this element, we check that the second element and the first element are not equal to it. We try and look for an element that is equal to it. And then for this element, we search all of these elements up until it, checking for an element, checking for one that equals to the element that we're currently on. We obviously don't find it. And then for this one, we search again, we don't find it. And then for this element, now we can see, but the algorithm now checks all the ones that are less than it, and it doesn't find, right? It doesn't find because we only check the ones that are less than it. And then this one, we check all elements that are less than it, and so on and so forth until we get to some sort of element that we already have seen. So now we get to this element that we've seen, and we check all the elements before it. Because it checks all of these elements, it'll also check the element that we just got to, and therefore we find our element that is the start of the cycle. And then we return it. Now the runtime of this, you can see on the top, is O of n squared. But that's because every iteration j, we check all the elements before it. Therefore, it's for the first element, we check 1, for the second element, 2, so on and so forth until n. In actuality, it's really until n minus 1, because the first element, we don't check anything. It's just the second one, we check the one before it. So, but just pretend again like it's smaller or equal, which is theta of n squared. If you want the more tight analysis, you can do it until n minus 1, but which is still theta of n squared. All right, now this it comes up a lot, this checking each element and checking all elements that came before it. It comes up a lot in these types of questions with linked list. It's a very useful tactic. So just try and remember, even if you don't remember the exact solution for this or for the merged linked list, like traversing it one by one for each element up until it is a really good strategy of solving these problems. Now we want to do it in O of n, kind of like our extra storage. But now we don't have linear um, memory, so we're going to do it in a different way. Um, this is a very, very classic problem, and it's a very classic solution. If you already know it, then good for you. But for those of you who haven't seen it yet, it's very, very, very cool. So we're gonna guess only for j's that are some sort of power of 2. Sorry, this is before the very well-known solution. First, we're gonna do a different solution. So let's guess for j's that are only the powers of 2, right? Kind of like the exponential search. This comes up a lot. You first check for each element, all the elements up until that same element, and then you just turn that into exponential search, and you only check powers of 2 and all the elements up until those powers of 2, and it decreases the runtime from O of n squared to n to O of n. So let's just see how that works in this case. It's just going to stop at some sort of to the power of j that we'll find. It could be that we skipped this first element. It could be we skipped it and then we got to this element after iterating a few times around the cycle. And we get to this element and then we check all the elements and we found that this element um, is actually part of the cycle. But we don't know that this element is the start of the cycle, right? The algorithm has to find the start of the cycle. This element is not necessarily the start of the cycle. Therefore, this algorithm is not uh, uh, adequate solution to our original problem. First is just let's see the runtime. It works in O of j times, so 1 plus 2 plus 4, because we check powers of 2, up until 2 to the power of log n rounded down plus 1, which is theta of n, which is a great runtime for finding if there exists a cycle. But if we want that first point of the cycle, that first element, it doesn't find it. Okay, so now finding it, finding that element, what we can do is we can just take, once we find that element that we know is part of the cycle, we'll pretend that it is the end of the linked list. And then what we'll do is we'll, exactly like the previous question with two merged linked lists, that two linked lists that are merged, we can find the point where they merge, right? We can just run that algorithm and find that first cycle. And now it's just a little side note that we don't actually have to delete this pointer. Let's say if you wanted to keep the original linked list with the cycle, we can just save this element, and the second we get to that element, we stop the first linked list. And that we start the second linked list from here. We don't actually have to change this pointer to null and cut the linked list. But it requires the sustaining of the uh, sorry, but what's important here is that if n is extremely, extremely, extremely large, then we need to keep track of that same index, right? We need to keep track of the index that we're searching, 2 to the power of I, right? It could be that 2 to the power of I is extremely, extremely, extremely large. And to hold that, we don't have enough memory, right? We need to save that in the memory. It could be we need a lot, a lot, a lot of memory, which is what we were trying to avoid. So therefore, this solution um, wouldn't be an adequate solution to our problem because we'd be using linear space or logarithmic space instead of constant space, right? If it was kind of like we saw in Divide and Conquer, if a number is extremely, extremely big, we need more than, we need a lot of space, and therefore it would not be constant. Okay, so now this is the very popular, very famous algorithm. It's Floyd's algorithm. You'll see also more algorithms of his in the algorithms course. But this is a very, very cool algorithm. It's called the turtle and the hare, right? Everyone knows the story of the turtle and the hare, where they raced and the turtle won because the hare fell asleep. This is a little bit different. The turtle and the hare are two pointers. They're basically pointers that are going to traverse our linked list. At every single iteration, the turtle is slower, so he's going to traverse each iteration just one. He's going to increment, he's going to go to the next element. And the hare is actually going to skip elements. It's going to traverse two elements at each iteration. So the hare is going to go faster than the turtle. Um, and this you'll see is going to help us find if there exists a cycle. And if there does exist a cycle, we can do something that can then find that beginning of the cycle without saving the index. We're just going to have two pointers. If there's no cycle, the hare is going to get to the end of the linked list, and we can return that there's no cycle. But if like else, um, there's some sort of cycle, right? And therefore they're going to continue the turtle and the hare are just going to continue traversing it, right? But we're going to prove that there's going to be a point where the hare and the turtle are going to collide. They're going to be on the same element, and then we know that there is a cycle. So first, at some point within the cycle, we know the hare has to pass the turtle, right? Because at some point they're both going to be in the cycle. Even though it takes the turtle longer, the hare's still going to be in the cycle. Um, and because the hare moves faster, the hare is going to eventually catch up to the turtle. The turtle. So let's just see an example. These are our two pointers. The hare each time um, traverses two, and the turtle each time one. Now the hare entered the cycle. And now the turtle entered the cycle, and the hare just keeps on going within the cycle because it's a cycle and you can't ever escape it. It's never ending. So now you see that hare has to catch up to the turtle. And as we can see, the turtle, like the hare, once it catches up to the turtle, has to collide with the turtle. Why? Because the difference here, we're going to do that here. Um, First off, the hare, I'm just going to say it actually verbally. The hare each time traverses two, and the turtle each time one. So the difference between the two of them is always going to be one. So the distance between them, each iteration, once they're both in the cycle, the distance between them, which is now two, will always decrease by one, because the hare will skip two, and the turtle will increase one. So therefore, the distance is now one, and then the distance will be zero. The hare cannot skip over the turtle, because each time the distance is growing smaller by one. So what's the runtime of this algorithm? Until the first point that the turtle is within the cycle is O of n, right? Because n is the size of the linked list, therefore it's definitely less than n. From the minute that the turtle is in the cycle, the hare is also in the cycle, and from the minute that the turtle enters the cycle until the hare passes the turtle, every iteration until the point where they meet, the distance between them um, is gets smaller by one each iteration, like we just said. Therefore, after O of n iterations, once they're both in the cycle, the turtle and the hare will collide. Therefore, it's O of n for the turtle to enter, O of n for them to collide. Therefore, O of n um, steps in total, and therefore the runtime is O of n. But now we found a point, right? The same problem as the previous solution where we didn't find the starting point of the cycle. We only found a point in the cycle. So now how do we find the starting point in the cycle? So this is going to be a separate algorithm that we're going to initialize two turtles, one from the beginning of the linked list, and the other one starts from the point where the hare and the turtle met. At every iteration, both of the turtles will move just one. Both pointers will move one element. And the second that they meet, will return that that element is the first point of the cycle. Now, why is that true? You can think about it. First, let's just see. We start initialize the turtle here and the turtle here. If the two turtles don't meet, that means that they'll never meet, right? Because one of the turtles will be, let's say, if the second turtle gets to here when the first turtle is here, so then they'll always increase by one, and they'll never, ever, ever meet. So therefore, if they do meet, then we know they have to meet in the first place. Like this is the first point that they'll meet, because then they'll both move together, right? So either they never meet, or they meet and it has to be here, and then they move together and they're always together. Okay, so now let's just see a little example. To increment each one by one, we'll move each pointer. I skipped the animation. We increment each one by one. And then, as you can see, they meet in this example. But now we need to prove for every single example, they will meet. And it's connected to what I just said about if they do meet, it has to be here. If they don't meet, then they will never meet. But if they do meet, it has to be here, because then they will move together. Okay, we have to prove that they will even meet, like we said, and then prove that the meeting point is the start of the cycle. I just said that verbally, it just they move together within the cycle. So if they meet, it has to be here. But let's do that now. Let's denote with by x the um, number of steps that the turtle does in the first stage up until the point where they meet, right? So that's the point where they meet. And then also the amount of steps that the turtle did is x. So the number of steps that the hare does is 2x, right? Because it always does 2 steps per iteration. If there's x iterations, then the hare did 2x. So therefore this point is also x distance from the beginning and also 2x distance from the beginning. Therefore, at the point, it's also has the number x and also has the number 2x, like we just said. After x steps in the second stage, the first turtle will be x from the beginning, right? So the first turtle is going to be at the meeting point, and the second turtle will be distance x from the sorry, they both start from the beginning. Once we start the next part of the algorithm, the turtle starts in the beginning and the next turtle starts at the nikuda, the point where they meet, right? So the first turtle starts here and goes x steps until it gets to this meeting point. And the second turtle starts from here and moves x steps, but therefore because it started from here, we know this is x, and then it does 2x steps. So therefore it'll also get to this point, right? So the first turtle does x, gets to here. The second turtle, it starts here, does x more, and we know that it'll end up here because of the hare. It also did x steps. And therefore, we know that they meet because this is also x and also 2x, right? So if the first turtle does x steps, second turtle does 2x because it did x before the second stage, and then the second stage does another x, 2x. They meet at the same element, at the same node. So what happened in the previous one? So we know now that they both meet, right? We know that they meet at the meeting point of the hare and the turtle, right? Um, because the turtles is what we said verbally earlier, because the turtles move together, because they both increment by one, that we know that if they meet here, that means they were together also at this point, because they both, one iteration backwards, they're both here, and one iteration backwards, they were both here. And then one iteration backwards, one of them was here and one of them was here. So the first meeting point has to be the meeting point of the cycle. So from the second that the second um, that they meet, they have to be together always. So that therefore the first place that they were together is the first point of the cycle, right? Because they move together. All right, another question. We're seeing that we're running out of time. So to sum, we're given a group of S, which equals x1, x2, and xn. We're given a group of n elements. We need to, this is the same thing as we did in, if you remember from hashing, we solved this, But here, we're just going to do it in other ways that are not hashing. So we need to propose a data structure that supports building the data structure and also um, gets us the two elements that are equal to this y. So we can call it multiple times. It might not be one time. We might be able to call it multiple times with different y's. So it's a bit different than the hashing solution that we saw earlier, but you can still use the hashing solution. So first, that the naive way, without doing anything in the initialize and the build, we just have n extra space, and all that we're doing is we're just going to check for each element. We're going to check all the other elements and check if they together sum up to y. And therefore, the runtime would be n squared, because for each element, we check all the other elements, which is O of n squared. This is if we prepare the the data structure, what we're going to do is we're going to calculate all the different sums. So we're going to calculate all the different sums, which is n squared, and we're going to put them in an array. And in that array, what we're going to do is we're going to sort the array. And once the array is sorted, we're going to we can binary search or exponential search on it. Let's just say binary search. And therefore, we can find any sum in log n squared, which is just log n time. So I hope that was understood. If not, try and listen to that again. But I have to continue onwards with these were the two naive ways. This one is naive without pre-computing, and this one is pre-computing all of the different answers. So these are both extremes to different sides. But we want something that has some pre-computing, it has some runtime in the build, in the initialize, but the query time is also not so large. So let's see this first solution. We're gonna first keep all the elements, our original elements. In this solution, we took all the sums and kept them in an array. Here, we're gonna keep the original elements in a sorted array. We're gonna sort the original element, and then we're gonna be able to do the query in n log n time. How are we gonna do that? For every element, we're gonna check if the y minus xi is within S. With binary search, it's very similar to the hashing problem that we just check if y minus xi is within the hash table. But here we're checking if it's in the array with binary search, which takes log n time. So we're checking for each element, n different elements. Each one has log n time. Therefore, it's O of n log n. So let's just see what we just saw. Just in the table, a little bit clearer. What we just saw is that it takes n log n to build because we're sorting the array. It only has n space, but the query time is n log n, which is really, really bad. Let's try and see if we can get this down. Just a reminder also, when we did this with hashing, it was just O of n time. But this was n log n amortized, because not n log n, it was O of n amortized. We'll see that I added another row to the table at the end. But let's try and make this query time a little bit better to O of n. So we're going to do the same thing. We're going to sort the array. But now we're going to do query in O of n. How are we going to do the query in O of n? We're not going to use binary search because it's a little inefficient. We're going to find two indexes that are equal to that same y we're looking for. We're going to have a left and an h, which is, what we're going to do is we're going to have two pointers that are going to traverse our array. And we're going to do it in a smart way such that it'll be, at worst case, O of n moves. And until we find two indexes that are the sum of them equals to y. So we're going to try and find those two indexes. So we're going to start with 1 and n, right? if 1 and n, the elements at 1 and the element at n, are equal to y, we're done. If they are smaller than y, then we know that L has to be greater than 1. L can't be 1 because it's the smallest element and this is the greatest element. So therefore, this smallest element cannot be with any element that's bigger because y is bigger than both of them together. So the only way we can increase this number is by moving um, the smaller pointer to something bigger. And the same thing if the sum of them two is larger than y, then we know that this n is too big. And the only way we can decrease this sum is by moving this to the left, decreasing it by 1. So therefore, in a recursive way, we're gonna keep on erasing a specific element that cannot be in the sum because we checked already all the previous elements that are larger. And so therefore, the only way to make it smaller is by decreasing a of n. Here, let's just see the example. So let's say we're searching for a sum that is 24. So we initialize it with our low and high pointers. And we're going to check the sum of both of them. The sum is 28, which is larger than 24. Therefore, we need to decrease the sum. The only way we can decrease this sum is by decreasing this pointer. 27 cannot be within the sum because 27 plus the smallest element is already larger, so it cannot be this one. So we can cancel this out and we can recursively operate on the high pointer now at 25, and we see it's bigger. So therefore we can decrease this pointer again because 25 plus 20 plus 1 is 26, it's larger. 20 plus 1 is now 21, which is smaller than this. So the only way we can increase this is by increasing our low pointer. Now, note that once we cancel out, let's say we cancel out some of the numbers here, and then we increment this pointer, we know that this element cannot be part of the two sum because we already tried all the options that could be already above. So therefore we increment this pointer, and 1 cannot be, therefore 1 cannot be in the two sum. And so we continue on now. 23 is smaller than 24, so we have to increment the lower one. And now we found 24, so we return them. It's a very, very cool algorithm. It's very, very useful in certain cases. Here's the pseudocode. The complexity of the query is for every iteration, the distance of h minus l, the high pointer minus the low pointer, gets smaller by 1. Therefore, it's O of n. And each time we do O of 1, right? You can think about it as a recursive formula. T of n equals T of n minus 1 plus O of 1. And therefore, if each time we only do O of 1 and we keep on erasing one element, therefore it is O of n. Now the space is just the array, and the time to build it is still we have to sort the n elements, which is O of n log n. Now here's a table summarizing what we just saw. We have the naive way with no pre-computations, pre-computing all of the different answers, all the different sums, takes that amount of time for each build, the amount of space and the query. And then what we just saw is n log n to sort, n space, and O of n for the query. And now the solution we saw in a previous recitation with the hashing is O of n amortized to build. Sorry, O of n, this is a mistake, it's O of n expected to build, and therefore it could be in some cases worse than n log n. But what is really good about this one we just saw is if we're already given an array that is sorted, we don't have to sort it, right? If we're given an array that's sorted, we can look up the query in O of n time without building. So therefore the algorithm would not need to build, and it would happen in O of n time, worst case, as opposed to using a hash table, which would take O of n also, but it would take O of n expected. It would, which is not as good as O of n worst case. So if it's given to already sorted, this solution is actually better.